Yeah, so today we've got Robert Booth talking to us about complete ZX-calculi for the stabilizer fragment in odd prime dimensions. Take it away, Robert.
Yeah. So, yeah, this is a project which has been going on off and on for a bit of a while, actually. It's sort of, we started talking about this kind of stuff with Titouan over a year ago. Um, and at some point, we were speaking with various people like Cole, Comfort, we've discussed this with. Simon, I think John at some point had a little bit of input. So there's sort of a collection of a bunch of ideas suggested to me by different people which have gone into this project. It's globally sort of more or less inspired by the completeness results which were obtained for stabilizer fragments in the qubit case by Miriam and her co-authors and their co-authors, as well as Heine's work on the qubit ZX calculus and his completeness result for that in 2018. Now, having said that, there are, I would say, a couple of differences between our calculus or our calculi and that of Heine that I think it's worthwhile to emphasize. Firstly, basing ourselves off of the work which Titouan has been doing on the flex symmetrization, what he calls it, we were able to obtain calculi which recover the only connectivity matters sort of meta rule, which I think a lot of people view as central to the qubit ZX calculus and which was lost in the qubit case, or at least in these presentations of the qubit ZX calculus. And secondly, I think we have a presentation of the stabilizer fragment, and in particular the Clifford group, which makes clear a lot of manipulations which are present in both the qubit and the qubit case, but which, at least to me, it's not obvious where the intuition comes from when you're doing these manipulations. That's not to say or to sort of completely disparage Heine's work. In fact, I think the completeness result for the qubit case gave me a lot of confidence in believing that the axioms for the odd prime case that I've written down were sufficient to prove the completeness. Now, okay, diving straight into the subject matter, what do I mean by quantum computing in odd prime dimensions or stabilizer theory in odd prime dimensions? Well, the state space for what I will call a qubit is just going to be a p-dimensional Hilbert space. And in order to set up notation, we will decompose an arbitrary state or vector in this Hilbert space along an arbitrary chosen orthonormal basis of size p, which we'll call the computational basis, and we label these elements with the elements, or the elements of this basis with the elements of the finite group of integers modulo p. Now, we impose throughout the whole article in this talk that p should be a prime number, and really the main reason for this is that this makes this finite group of integers mod p into a finite field, and we use this in many places throughout the articles, although it might not be completely apparent why this is necessary in this talk. In order to manipulate these states, we have a set of sort of standard gates for qubit or qubit quantum computation. I think the most central and most important of these maybe are the Pauli gates. And the Pauli gates are generated by this pair of Z and X operators. The Z operator is a diagonal multiplication by a phase. The phase is a pth root of unity, which will denote omega throughout the talk, and we weight this phase in the exponent with the label of the basis state on which we're acting. The X operator acts on the basis, the computational basis, as translation through the basis elements, modulo p. And then we call a generic Pauli as just any ordered product of these two operators weighted in each in some element of our finite field. The collection of all of these things we'll call the Pauli group, and this is standard for qubit quantum computation. Connecting these two representations, we have a Hadamard gate or Fourier gate, which really is the generalization of the Hadamard gate to qubits, and also corresponds to the Fourier transform on the finite group ZP. But I think more importantly to this article, it connects the Z operator to the X operator under conjugation. Acting on sort of pairs of qubits, we have a generalization of the controlled phase or CZ gate, which also acts as a weighted pth root of unity, weighted in the labels of the orthonormal computational basis. And then we have a phase gate, which is also multiplication by a weighted pth root of unity, but now where the phase is parametrized by a quadratic polynomial in the labeling. Now, there's just one sort of element of ambiguity in this notation in what the meaning of this 2 to the minus 1 means. And throughout this article, these 2 to the minus 1s are going to appear everywhere, and they should be interpreted as multiplication by the inverse of 2 within the finite group of integers mod p, and not division by 2 in the reals within this exponent. Now, these are sort of different things. In particular, dividing by 2 within the reals would, in some cases, not in this one, but in some cases, take us out of the group of pth roots of unity. Now, a key difference with the qubit case is that these gates are not self-inverse, and in fact obey different relations, unsurprisingly I suppose, to the qubit case. But for all of the Paulis, the phase, and the CZ gates, they obey this relation where if you apply them p times, you get the identity. And then even the Hadamard is not self-inverse. You have to apply it 4 times to get the identity back. And this is something which is going to play, which plays a fairly important role in a lot of the proofs. Now, having introduced these sort of standard gates for quantum computing with qubits, let's define the qubit stabilizer fragment. So if you remember from the qubit case, the stabilizer fragment is defined as the fragment of quantum theory which you can get using just initializations of Pauli states, Clifford unitaries, and projections onto Pauli states. By the way, I forgot to ask at the beginning of this talk, can you see my mouse?
Yes, we can.
Brilliant. Not been pointing at nothing that you can't see. Perfect. In the qubit case, we are going to take exactly the same rule for generating the stabilizer fragment. We replace our we will replace our Pauli states with the Pauli states for the qubit for p-dimensional Hilbert space, which are the eigenvectors of the Pauli operators I just presented. The Clifford unitaries are defined analogously to the qubit case as the normalizer of the group of Paulis in the group of unitaries acting on the Hilbert space. And you can, sort of unlike the qubit case, you can give a particularly, I suppose, clean high-level presentation of this Clifford group in the following form. You can think of it as an affine transformation which acts on the labels of the Paulis, so these pairs A and B, where you have a linear part, which is a symplectic matrix, an affine part, which corresponds to translation, i.e. just applying a Pauli, multiplying by a Pauli operator, which sums into the exponents. And then some global phase, which you have to take into account when you are looking at the action of this group or the representation of this group in the Hilbert space. So formally, you can think of this as the Clifford group on n qubits as a representation of the affine symplectic group over the vector space of dimension 2n with some global phase term. Now, in reality, we're actually going to axiomatize a slightly smaller fragment of quantum theory, and I'm not really going to go into the details, but it just comes down to the fact that this torus, which contains this global phase part of the Clifford group, is uncountable, whereas we wanted to get a finite axiomatization, and so our calculus can only represent a countable set of these phases, precisely which I'm not going to go into, but it is characterized thoroughly in the article. Okay, so that was stabiliser theory in prime dimensions. We can dive straight into the calculus itself. These are the generators of the calculus. I don't think there's anything which is particularly surprising here. They're all essentially what you would expect from coming from the qubit ZX calculus, with, I suppose, two small exceptions. The first is that the labels or the phases of the calculus are no longer elements of the torus, but instead are pairs of elements of our finite field ZP, which are going to parameterize a phase, essentially, in the unitary part of the calculus. The X part is going to correspond to a Pauli operator. So the X part is going to correspond to Pauli operators in the corresponding basis. And then the Y part is essentially what's left over from the Clifford group when you exclude the Paulis. And so I typically refer to this as the pure Clifford part of the spider, or of the phase. And then I also had to include an additional scalar generator, the star here, which, as we'll see in a few slides' time, was a bit of a kludge to solve a problem to which I couldn't find a clean solution to, or a cleaner solution. Now, having given these generators, we can define spiders just as you would within the normal ZX calculus, at least for the green parts. They're defined inductively on the number of legs of the spiders, as usual. The red spiders are defined in the same way as the ZH calculus beetles. That is, we have, in addition to this usual inductive definition, we have these antipodes that appear everywhere, or these one-to-one red spiders that we call antipodes. And in a sense, this is the price, or maybe one of the prices we pay for recovering this only connectivity matters rule, is that we have to put these antipodes everywhere in the calculus and take care of them independently. Now, at some point, I suggested that these red spiders ought to be called red ants, but I don't think that this ever made it into the final version of the article. Given this definition for the phaseless spiders, we can then define the phased spiders in the same way as you would for the qubit ZX calculus, by composing with a phased unit. And for the red spider, analogously, but once again, we have this extra antipode that we have to add in for the construction to work. Okay, so this is sort of the set of all generators for the calculus. This is the standard interpretation of these generators into Hilbert space. I'm not going to I don't really expect you to parse this whole definition and sort of internalize it in the short amount of time I'm going to stay on this slide. But I do think it's worthwhile to point out a couple of details. So when I define this interpretation, I use this notation K semicolon Z to describe the eigenvectors of the Z operator, which in this case correspond to the computational basis we had earlier, and analogously for the eigenvectors of the X operator. So a couple of points. The first one is that we have these, once again, these 2 to the minus 1 multiplying all of the exponents of our phases. This really is a sort of trick. You could, in principle, if you were not interested in the scalar fragment of the language, remove all of these 2 to the minus 1s, and you might have to modify a couple of the rules a little bit, but you would get a perfectly equivalent calculus. But this 2 to the minus 1 is a trick for getting a cleaner or a smaller presentation of the scalar part of the language. And we'll see what I mean by this in a few slides' time. The second point to note is that on the output cats for every red spider, there is this additional -1 within the output state. And this makes it so that, as we'll see, the antipode in the qubit ZX calculus is not trivial. And therefore, when we had all of these antipodes in the previous slide, they are not, we cannot remove them or eliminate them. And as you'll see, for each of the red spiders, this is the case. As for its operatorial version, the Hadamard box also interprets as the operator which takes the Z basis into the X basis. And then we have the final interpretation for this Kludge spider, which interprets as -1. And it turns out that the scalar -1 is a little bit tricky to represent in some dimensions, as we'll see. Now, given this interpretation, we can calculate the interpretation for spiders, which I think are reasonably unsurprising given the qubit ZX calculus. For the phaseless green spider, we once again have this, essentially this relation which forces equality on all the legs of the spider. And then when we introduce the phase, we multiply by this diagonal phase, once again parametrized by a quadratic polynomial, right? So we have this x part which is linear and the y part being quadratic. Once again, the x part will correspond to the Pauli operators and the y part is the non-Pauli pure Clifford part. The red spider is completely analogous, except we have we're now acting in the diagonal in the x basis, and we have this additional minus as always. The other thing that we can calculate, given the definition of this interpretation, are the following 3 operators. We get, for the 1-1 green spider, the phase gate. The Hadamard interprets as the Hadamard. And then we have, just like the qubit case, the CZ operator. It turns out that these 3 operators plus the Pauli states, or even just the 0 Z state, which I haven't written the diagram for, but it's just a red unit with an antipode, is sufficient. It's sufficient to generate the entire these guys are sufficient to generate the entire Clifford group, and so therefore, if we add the Pauli 0Z state, then we have something which is universal for the entire stabilizer fragment. Okay, are there any quick questions on the interpretation itself before I move on into the axiomatization? Okay, seems like not. In that case, on to the axiomatization. Now, the first set of rules, which I feel like we should mention because they didn't necessarily hold in for example, Heine's qubit ZX calculus. We have what Titouan refers to as structural axioms, which essentially encode this only connectivity matters rule. So we have pretty much all of the equations that you would expect to hold for the swap gates in the calculus and the swapped and the cup and cap. And then we have this additional flex symmetry equation. And what this says is that if you take any generated G of the language, turn it into a state via map state duality, then any permutation of the outputs of that state should leave the state invariant. And this means basically you can sort of drag this generator anywhere around in your graph. As long as its connectivity stays the same, its interpretation stays the same. And therefore, you can really treat the whole calculus as a graph. I should add, in case it's not completely obvious, I hope it is, but that all of the axioms I'm going to present are, of course, sound for the interpretation I just gave. So the upshot of this is that the calculus is flex symmetric, and we can really treat any diagram as just a labeled graph, where if I ever need to calculate the interpretation, I just map it back to any equivalent representation within the formal generators and use the functoriality of the interpretation. Moving on from these structural axioms, we have what I think of as standard ZX axioms, which are also, I think, more or less what you would expect. A few things which are worth pointing out. In the fusion rule, when we fuse two spiders together, because we no longer have phases which are elements of the torus, but instead these ZP square groups, we just sum along the product of the groups in the label. The characteristic equation up here, which you might think of as a generalization of the Hopf equation, now is a sort of p-legged version of it, and essentially it just picks out the dimension p of the Hilbert space. The copy equation, once again, copies the Pauli the Pauli states in the calculus, just like in the qubit case. And then I think, as I mentioned a bit earlier on, the antipode is no longer trivial, but it is an involution. So if you apply two antipodes in a row, this is the same as if you'd done nothing. So this is sort of the usual axioms for the ZX. And then we have a series of axioms which are used to axiomatize essentially the unitary group, or the Clifford group. And so this equation, which I call shear, essentially encodes two equations for the sake of sort of minimizing the number of equations that we use. And so if we first take d equal to 0 on both sides of this equation is essentially giving you the phase that you get when you commute two Pauli operators. And then if we take c, if we set c equal to 0 and d different from 0 and n, it is giving us a relation between the green Pauli operators and the red pure Clifford operators. In terms of these affine representation of the Clifford group, you can think of it as the following equation. That is, it's saying if I have some Pauli and I do a translation which corresponds to putting a Pauli, sort of applying a Pauli on this state, and then do the symplectic part of my Clifford, which in this case for the spiders is always just a shear. This is the same as if I'd done the shear first and then done a translation, but where now I have this additional term in my translation because the shear has to act on the original translation. Right, so this is just a usual commutation relation for affine linear operations. Then we have a couple of... you're still really robotic, unfortunately.
Yeah, I don't know what to do about it right now. Can you understand me?
Do you want to put your question in chat, maybe? That might be easier, if it's not too long.
Sure.
Should I stay on this slide?
Yes. Do you see my question?
I can't actually read the question, so someone has to read it out for me.
Okay, so it says why A0 and A0 instead of A0 and minus A0. So John would expect there to be an adjoint in there.
Because I sort of, to make the equation a little bit smaller, it comes down to the fact that there is this -1 on the sort of output side of the red spiders. And so when you send the spider, a green spider, through an antipode, it picks up a minus in the Pauli part. Yeah. So this is intentional that there should be just a positive A on both sides. Okay, I hope that answers the question.
John says thanks.
Perfect. So then we have a pair of equations which axiomatize what I call multipliers, which are these essentially these z-legged versions of what you might think of one side of the hot equation. And what this first equation what I use for eliminating multipliers is saying is really just that the multiplier enacts the following operation on the computational basis. That is, you multiply by z within the ket, and we impose for both of these equations that z should always be non-zero, so that it is unitary, z is invertible, and so on. And because the phase in these co-units is linear in the Pauli part and quadratic in the pure Clifford part, then we get a sort of linear z popping out from the Pauli part and a quadratic coefficient popping out from the pure Clifford part. Now, there's a little bit more packed into this equation purely for the sake of sort of eliminating equations that can be packed into one, but this is the general idea of what's going on in this equation. The second equation is describing how to decompose the multiplier in terms of the invertible one-to-one generator of the language. And once again, I think that this equation is best thought of in terms of the underlying symplectic matrices. And it's just saying that the multiplier corresponds to this z-1 diagonal matrix. And you can decompose it in terms of the symplectic representation of the Hadamard and then a sequence of 3 shears. And then you also need to recalculate what the exact phase difference is between both sides of the diagrams in the representation. Once again, this affine representation of the Clifford group never takes into account the phases. Okay, so this is more or less the core of the language. And then we have a handful of maybe somewhat ugly axioms for the scalar fragment of the language. We have a scalar which essentially is saying that the square root of p times 1 over the square root of p is equal to identity, or to nothing to 1. And we have a labeled version because this enables us to eliminate this label in a party graph. I believe, so I came across a proof in one of Miriam and her co-author's article that you can get rid of this, and I assume that this works here. I just missed it when I was writing the article. We have a rule for the diagrams which interpret as 0, which is essentially diagrams of these Z0 diagrams are essentially ket, the Z eigenvector of Z acting sort of in a product with the 0 eigenvector of Z, therefore it's just a 0. And these equations, just like in the qubit case, just allow us to sort of cut up any diagram in order to prove that every diagram that contains some 0 diagram is just the canonical 0 diagram. And then we have a sequence of equations, or 4 equations, which are used for taking care of the pure Clifford scalars. Because this pure Clifford scalar here is a little bit tricky. In the case where Z is different from 0, it's essentially a Gaussian exponential sum. That is a sum over the pth roots of unity, but within the exponent, there will be a quadratic term. And these are a little bit finicky to take care of, especially diagrammatically. They're sort of, I think, one of the motivators for very early number theory was Euler trying to calculate the value of these things. And it turns out that their value depends in a not particularly clear way on the prime p that gives us the dimension of the Hilbert space. And in effect, this rule here, the Gauss rule, is the rule that it is the reason why we chose to have this 2 to the minus 1 in the phases, because it allows for this clean this cleaner rule where we can do it for, we can write one rule for all non-zero values of z, where if we don't have this, it gets a little bit more tricky. We have to do more subcases. And what this rule is saying is that if z is not a square in zp, then it is equal to minus 1 times the value of this Gaussian exponential sum. And if z is a square, then it's just equal to 0 to the minus 1. And this is the chi of p is the characteristic function of the complement of the set of squares in zp. Then, in order to eliminate these minus 1s, we need a rule for multiplying 2 minus 1s together, which gives us just 1. And then, unfortunately, even this is not enough, because in some dimensions, in particular, when p is congruent to 1 mod 8 or 5 mod 8, which is equivalent to it being congruent to 1 mod 4, the 0, 1 exponential sum is either plus or minus 1, but I couldn't find a clean way to decide which one it was, so I just had to impose an additional rule to get this. So just a quick comment about this. I'm not going to go into any more detail on the completeness of the Scala part of the language in this talk, simply because there's not really enough time and it's rather technical. But I do expect that you can probably do a lot better, but you can probably do better than these 4 rules. I just haven't found the right formulation to do it. Now, if we ignore the Scala part of the language, we end up with an axiomatization, which is something like this, which I really don't think is too bad. I do think there is possibly some redundancy in these equations that axiomatize the C1 group, but it's a little bit tricky for yet again for reasons I don't really have time to go into. And if we sort of want to reintroduce the scalars in terms of sort of their interpretation, we end up in an axiomatization like this, where we have these phases that come out from commuting Pauli operators with Pauli operators in the other basis, or with pure Clifford operators in the other basis. And then this multiplier with the interpretation of this Gaussian exponential sum, which is this, which I've denoted by this symbol, but is not a particularly clear relationship and really depends a lot on the value of p. Okay, so are there any questions on the axiomatization before I go any further? Okay, it seems like there aren't any questions, so I forge ahead. So these axioms are sort of the smaller set of axioms that we managed to reduce our set to derive all of the others. But in practical terms, there are some sort of more useful axioms that you are going to use to argue about anything in the language. The first of these is that 2 of the Hadamards in a row, like I said, the Hadamard is no longer an involution, but 2 Hadamards in a row are equal to the antipode. And this has some consequences, specifically when you try and recover a version of the color change rule. Now, I'm not going to go into that because it's a little bit tricky to formulate, but we do have a version of the color change rule that holds in this calculus. But it does have, it sort of involves a lot more manipulations than just changing the colors of every vertex. We also have a sort of second version, what I think of as the true generalization of the Hopf rule from sort of Hopf algebra, which is pretty much what you expect if you're familiar with that. We have a rule for eliminating phases on the opposite color, which should really just be any phase, not just x0. And then we have a bunch of rules for moving Pauli operators throughout the graph. So we have a Pauli copy. We have this relationship, like I said, where you end up with a -1 on the Pauli part of the green spider when you send an antipode through it, and analogously for the red spider. Now, I think maybe a more interesting derivation, and this follows essentially from the multiplication rule that I was just telling you about. We have a Euler decomposition for the Hadamard gate, which I think is rather nice. I'm quite happy with this. It's pretty clean, I think, Euler decomposition. And then we also have some slightly trickier rules. We have a rule which allows us to change the color of some pure Clifford states. There is a phase here which I've chosen not to write. But I think the more interesting part here is that this rule holds only when the label of the state is a square. And so we get again more number theory coming into sort of any argument you want to make within the calculus, simply because if I want to apply this rule to any a given state, I need to first decide whether the label is a square or not within the finite field ZP. And so then you're immediately in the field of elementary number theory, and you have to use things like quadratic reciprocity and these kinds of arguments that follow from that. I think another interesting rule that I've chosen to make here is, and I think which is particularly representative of some differences in the calculus, is that in the qubit case, there is, you can show that these Hadamard loops, there shouldn't be an x here because I haven't introduced these yet, but just think of this as a normal Hadamard and x equal to 1. These Hadamard loops are equal to Pauli operators, whereas in the p-dimensional case, we now have something which is pure Clifford. And in fact, this makes it so that some of the derivations which are used to simplify the calculus in the qubit case are not usable because they rely specifically on this relationship between Hadamard loops and Pauli operators, which we don't have. And this, in some sense, exhibits another difference, which I probably didn't emphasize enough earlier on, is that you really have independent Pauli and pure Clifford parts in the calculus, unlike in the qubit case, where the Pauli group can be thought of in some sense as a subgroup of the pure Clifford group, or whatever you want to call it. I think the analogy doesn't really work at that point. And so you really have sort of these two cyclic groups which don't really interact in the diagonal fragment. So moving on from this, we have some nice, so we're able to recover some of the meta rules from the Spider Wars stuff. We already saw that spiders of the same color fuse and you sum their phases. We have a sort of an analogous rule to the qubit rule for cutting edges, except that now edges are cut mod p. And furthermore, you also need to take into account edges that have antipodes along them, because these are no longer trivialized in the calculus. And so given that these multi-edges seem to be of some importance, and in fact it's quite useful, we went ahead and introduced some syntactic sugar for representing these multi-edges in the calculus. And so defined what I call really the multipliers, which are these guys here. And these are defined inductively as essentially the Hopf, once again, this sort of Hopf-like diagram, or sort of one side of the Hopf rule, where I now have m+1 or m edges or m legs on that diagram. And I've included scalars here simply so that these guys are normalized to a unitary operator, and this makes some of the diagrams in the calculus easier, but it's not particularly important. So given this inductive definition, we can see that the overall diagram for a multiplier is just this hop-like diagram with X edges. Now, one key point to emphasize, well, I don't know if key, but a point which is worthwhile to bring up is that once you introduce these multipliers into the language is no longer strictly flexometric, since these guys are not equal to their adjoint, I suppose, in the calculus, or their and this is something that so one reason why I didn't include these guys straight up within the generators themselves, because I wanted to maintain this flexometry for the language. Having said that, they are pretty useful for reducing the size of diagrams and making some arguments clear. Another thing to mention is that these multipliers correspond exactly to those which are defined by Fabio-Zanazzi in his thesis and in one of his articles on interacting Hopf algebras, if you're familiar with that, up to the normalization, since they don't consider normalizations, at least in Hilbert space, in the way we do. Now, these multipliers verify the following equations, which basically just say that the multipliers are a representation of the field ZP. That is, we have a rule for multiplying them, a rule for summing them together, a rule for multiplicative inverses, a rule for a rule which corresponds to the characteristic equation in terms of multipliers. That is, if I have a p-ary version of this Hopf on the left side, then this is equal to the zero diagram, which, if you recall from the previous slide, is just this cut edge. And the rules for representing the antipode as a multiplier, which it turns out is just equal to multiplying by -1, and then for the identity, which of course is just equal to multiplying by 1. And it follows from these rules that we can replace the label from the previous slide, which was an integer, with a label which is an element of the field ZP instead. This is somewhat more useful for making arguments. Building off of these multipliers, we can go a little bit further and define weighted analogues of the Hadamard gate. Since the Hadamard, when you commute it through a multiplier, just flips the multiplier, we can unambiguously define a weighted Hadamard by this equation, where we just pick one side to put the multiplier on, as long as it's always directed toward the Hadamard on the right-hand side. And this just corresponds to repeated H edges between these two green vertices, plus, as always, this normalization. And generalizes a construction which might be elsewhere, but which I first saw, at least in this article by Alex and Konstantinos, where they were considering the qubit ZX calculus, and they have a qubit version of this weighted Hadamard. Now, these weighted Hadamards are flexometric because of this equation for commuting the multiplier on the previous page, which means that we can also unambiguously define these weighted CZ gates, which correspond, to those of you familiar with the qubit theory, really to the weighted CZ gates that you would use in that case. In turn, they verify a set of equations which is a little bit maybe more removed or unfamiliar than the multiplier equations. I think one thing which is interesting is that if you multiply, or if you multiply or compose two weighted Hadamards, then you get a multiplier in the calculus. And the consequence of this is that you have a rule for eliminating these Hadamards and a rule for finding the inverse of a Hadamard, which it turns out is just -x. This might look like you're summing them, but you're really not. Yeah. Moving on. So these Hadamard can be used to construct a sort of particularly useful set of states in the calculus, which are graph states, which are exactly the graph states that you would use for MBQC and say the one-way model for qubits, and which really generalize the graph states that you have from the qubit case. That is, if you take some graph, you can construct a state which corresponds really just to viewing this graph as the vertices of this graph as red vertices, as green vertices in the calculus, and the edges as Hadamard edges weighted with the corresponding label of the edge. And these are really useful, and in fact are the core of the proof in the qubit case, and the proof of completeness for the stabilizer fragment in the qubit case, and for our proof of completeness here in the qubit case. So for an arbitrary graph, which is typically going to be given as its adjacency matrix, I'll use the following somewhat informal notation, which is defined more formally in the article to represent the corresponding graph state with the corresponding underlying graph. Now, we can give a sequence of nice rules for how these graph states interact with the rest of the language. The first is that we can give a version of we can give a rule for the stabilizers of this graph state. Namely, I think it's well known that if you act on this graph state by applying an x at some vertex and a z operator at every one of its neighbors, which in the qubit case needs to be weighted with the weight of the edge from this vertex v to this vertex w, then this is the same as if you'd done nothing. And so if you write this in the calculus, we just get something which says apply a red Pauli, which is just the x operation on some vertex, and then the corresponding weighted green Pauli on every one of its neighbors. And this is equal to the identity. Then we have a slightly more tricky, although not too difficult, operation for acting on these graph states. It turns out that if you're familiar with the qubit theory, when you look at these graph states, you can decompose any local Clifford in terms of any local Clifford equivalence of graph states into a sequence of local complementations acting on the graph. In the qubit case, this is a little bit more tricky because you need two operations, local scalings and local complementations. So the first of these is local scalings. And local scalings act by you pick a vertex in a graph and then you just scale every edge connected to that vertex by your scaling parameter here, gamma. And this, it turns out, is equivalent to sending a multiplier into the graph on the edge which corresponds to this vertex, the output edge. And so here we have precisely this equation stated within the ZX calculus.
Robert?
Yes?
Does this work for gamma equals 0?
It does not work for gamma equals 0. I should write gamma is different from 0.
Okay.
Gamma needs to be invertible.
Non-zero gamma I can apply.
Yeah, exactly. Then the second of these operations, which is a little bit more tricky to motivate, is local complementation, which really isn't much of a complementation at all in the qubit case anymore. In the qubit case, you have this idea of complementing the edges between the neighbors of your target vertex W. In the qubit case, in the p-dimensional case, we generalize this by the following operation. For every cone with head W in the graph, we add we sort of sum a weight onto the edge between the feet of the cone which is weighted by the value for the local complementation, the weight for the local complementation, and the corresponding weights for each of the edges. And this time this does work for gamma equals 0, but it's just the identity then, so not particularly interesting. So if we look at a more bigger graph, you just do the same operation for every possible cone with head W. And you can, so in this graph there's just 3 because I chose an easy example to write. And so you add an edge here for this cone, an edge here for this cone, and you add a weight onto this edge which already existed corresponding to this cone. Now, in terms of operators, this has a slightly trickier representation in terms of pure Clifford operators. And it turns out that doing the local complementation at a vertex W in the graph is equivalent to sending a red pure Clifford phase into the corresponding, on the wire corresponding to that vertex. And on every neighbor of that vertex, you send in a minus green spider weighted with the square of the edge weight between those two vertices. So it's a rule which is a tad trickier to apply than the qubit case, but not overall too difficult, I would say. So at this point, we're almost done with all of the sort of constructions which are used in the completeness proof. The last thing that we really need is the following. We need the completeness result for the single qubit Clifford group. And so what this is saying is that if you take any sequence of composition of invertible one-to-one operators sort of composed in a row, then we can rewrite any such composition into one of the 2 following forms. And furthermore, this form is going to be unique amongst the set of all forms in this proposition, in this statement. What this statement is really saying is that any single qubit Clifford diagram is going to be, once again, this transformation with a sort of linear part and a translation. And this is just a decomposition into shears and the sort of diagonal WW-1 diagrams plus a translation, or vice versa on the other side. Now, another point which is rather nice, I would say, about these diagrams is that they're very close, they are very close to the corresponding normal form that Miriam had for the qubit case. And I should have, but I didn't grab a picture of that. But if you compare these normal forms with the ones from Miriam's article, you'll see that they are indeed particularly close. And what this means is that it is pretty natural then to, at a high level, apply the same broad idea to the completeness proof as Miriam did in the qubit case. Namely, and I'm not going to give you all of the details because it would be far too long and a little bit boring, I think. We do the following sequence of steps. We first take any diagram and we turn it into a state using the usual map-state dualities. Then in a second state, we show that every state in the calculus can be rewritten to a form which is called graph state plus local Clifford. That is, you have a graph state, and then on each of the output wires of this graph state, you have basically a diagram like this acting upon that edge. then, using this normal form, we pull as much of this diagram as possible into local scalings and local complementations in the graph state part of the diagram. So the easy one to do is this W, which just becomes a scaling in the graph part, and then we can also pull in Pauli's and pure Cliffords using the rule for local complementations and for Pauli stabilizers. And we end up with a graph, or so a diagram which is called reduced graph state plus local Clifford, in which you only have some subset of the possible local Clifford operations acting on each of the output wires. And then if we take two diagrams and reduce them all the way to this reduced graph state plus local Clifford form, then we know how to compare two of these diagrams using some of the methods that Miriam developed in her completeness article. So at high level, we are pretty much following the proof from that work, although locally, pretty much all of the arguments need to be redone to suit the new calculus. But the upshot of it is that using this kind of argument, we have a completeness result for the scalarless part of the calculus, just as Miriam did. And then we have to take care of the scalar part independently, and this is a little bit more tricky. It involves a lot of these number theoretic arguments that I suggested in sort of the early parts of this talk, and which I don't really want to go into, but it essentially amounts to picking a normal form which depends on the prime p in a sort of inconvenient way, and then proving a bunch of multiplication rules for scalars using these number theoretic arguments. Another sort of pair of results which are in the article, but which I don't really have time to go into in any depth. Firstly, we have we use a construction that Titouan and Renaud and Simon developed for axiomatizing the CPM construction given the ZX calculus, which they called the discard construction, and which involves extending the calculus with a single generator, which is just a discarding construction, or a generator for discarding. And we show that then our calculus is universal and complete for mixed stabilizer states. And there's a nice bonus from this, based off of the work of Cole and Alex. They showed that you could also axiomatize mixed stabilizer states if you considered affine co-isotropic relations with a fairly similar calculus. And so we can define a new interpretation of our mixed qubit ZX calculus into the category of affine co-isotropic relations over the finite field ZP, which is now sounding complete for that interpretation. Okay, so that more or less summarizes the results which are in our article. There are, of course, a number of open questions which are left over. As I suggested when I was talking about the axiomatization, I think we can certainly do better in terms of minimizing the axioms, and I think there's a few that we can clean up as well. I'm also curious to see if we can find a nicer normal form like Miriam and Tom McElveny, I hope that's how that's pronounced, have done for the qubit case with their phase polynomial normal form. Then I think the real question that I guess a lot of people are asking is whether it's possible to do complete ZX calculus for all of quantum theory, at least in prime dimensions. And this seems rather tricky to me. One, I suppose, potential avenue is that in this article, the unitaries are parameterized by polynomials or quadratic polynomials in a single variable. The sort of obvious thing to do is to try and take higher order polynomials, but it's not clear that these will relate to each other in a particularly nice way, although it is known that for dimensions strictly greater than 3, these are universal already, or approximately universal, by the work of Mark Howard. However, having said that, I think the ZH calculus has a sort of more straightforward proof of universality in the qubit case than the ZX calculus, and it has sort of can be generalized naturally to the case of prime dimensions. So this is possibly a more tractable route for the universality proof. As for non-prime dimensions, this is possibly something which is there's reason to be more optimistic about. There is some group or representation theory of the Clifford group in non-prime dimensions which we might take advantage of, but it is considerably more complicated and less clean than the qubit case, the prime dimensional case. And on the other hand, these phase polynomials that I was just talking about are known in Hilbert space to the phase polynomial form is known to hold, I think, over any locally compact group. So maybe this is also a reasonable way to attack the problem. Then finally, I think there's one last question, which is, what about, we have an axiomatization for affine co-isotropic relations over ZP. What about other fields and applications of these affine relations over other fields? So with that, I've probably spoken for far too long already. So thank you for paying attention, and I'm very happy to take any questions you have.